Today we'll be tackling the Chapter 18 study guide. So here we go. Okay, for this first section we are describing whether it's an acid or a base. If the property is for an acid, we write acid. If it's for a base, we write base. If it's for both, we write both. All right, what can turn litmus paper a different color? Is that acid or base or both? That is both, correct. Both can turn litmus paper a different color. Number two, which react with certain metals? An acid reacts with certain metals, and in the process it will produce hydrogen gas. Number three, contains more hydrogen ions than hydroxide ions. Which one is that? That's an acid. That's right. Acids contain more hydrogen ions than hydroxide ions. Which one feels slippery? Bases. Bases are the ones that feel slippery. Which one reacts with carbonates? Acids react with carbonates. We said in our video, as a matter of fact, that geologists will sometimes use an acid to detect the presence of limestone. Limestone is a carbonate, and so if they add a little acid to the stone and it begins to fizz, they know they've probably got some limestone in that sample. Okay, which one feels rough? Well, actually, we wouldn't really call either one rough necessarily, so we'll just put neither there. A base is kind of slippery, but acids don't really feel rough, so we'll just put neither. Which one contains equal numbers of hydrogen and hydroxide ions? Wow, two in a row. Two in a row. Neither. Yeah, that would be a neutral solution, wouldn't it, if it contains equal numbers of hydrogen and hydroxide ions? Which type tastes bitter? Now remember, it's important not to taste things in the lab, but yes, bases tend to taste bitter. And then finally, which ones taste sour? Right, the acids tend to taste sour. Things like vinegar or citric acid, definitely sour. Okay, moving on to the next section, where we have a word bank and we're filling in the passage. The blank model of acids and bases states that an acid contains the element blank and forms ions of this element when it's dissolved in water. Okay, a couple things there, and go. Right, the Arrhenius model of acids and bases is the one where it says that an acid contains hydrogen and forms hydrogen ions. A base, this is 12 and 13, a base contains the blank group and dissociates to produce blank ions in aqueous solution. Yeah, that's hydroxide for both blanks. According to the Arrhenius theory, the bases contain hydroxides and they dissociate to produce those hydroxide ions in aqueous solution. All right. According to the blank model, an acid donates blank ions and a base accepts blank ions. That's the Bronsted-Lowry model. Bronsted-Lowry. I don't have a cool little special O that I can type in there like they have in their word bank, but oh well. An acid donates hydrogen ions and a base accepts hydrogen ions in the Bronsted-Lowry model. According to this model, in an acid-base reaction, each acid has a blank and each base has a blank. That's right, each acid has a conjugate base and each base has a conjugate acid. All right, page 2. This is along the lines of the strengths of acids and bases, so we're circling the best statement that answers the question. Acid A and acid B are of equal concentration and are tested with a conductivity apparatus, sort of like what I did in the video. When the electrodes are placed in acid A, the bulb glows dimly. When they are placed in acid B, the bulb glows more brightly. Which of the following is true? Is it acid A is stronger than acid B is stronger than acid A and acid B are of equal strength, or no comparison of strength can be made from these results? The answer is acid B is stronger than acid A. Remember, we said that strong acids will dissociate better and give more electrolytes in solution, so therefore that's why the bulb glows more brightly. A chemical equation for the ionization of an acid uses a single arrow to the right to separate the reactant and product sides of the equation. Which of the following is true? Is it A, the arrow does not indicate relative strength, B, the ionizing acid is half ionized, C, the ionizing acid is strong, or D, the ionizing acid is weak? It's C, the ionizing acid is strong. Remember we said that for strong acids there is very little, if any, reverse reaction, and so therefore it's pretty much a forward reaction only. Sulfuric acid is a strong acid. What is true about its conjugate base? Is it its conjugate base is amphoteric, its conjugate base is strong, its conjugate base is weak, or no conclusion can be made regarding the strength of the conjugate base? The answer is C. All strong acids yield extremely weak conjugate bases. In fact, they're so weak that we talked about how they are unable to hydrolyze water. That was section 4 that we talked about that. In solution, a weak acid produces, is it A, a mixture of molecules and ions? Is it B, all ions? C, all molecules? D, anions but no hydronium ions? It's A, a mixture of molecules and ions. Weak acids will dissociate somewhat, but mostly they stay in the molecular undissociated form. Why are Ka values small numbers? Now, we did actually give a Ka value for hydrochloric acid, but that's not the usual case. We don't normally give Ka values for strong acids. We normally give them for weak acids. Why are Ka values all small numbers? Is it A, the concentration of water does not affect the ionization? Is it B, the equilibrium is not stable? Is it C, the solutions contain a high concentration of ions? Or D, the solutions contain a high concentration of unionized acid molecules? It's D. The solutions contain a high concentration of unionized acid molecules. Remember, K values will tell us if a reaction is product favored or reactant favored. So a Ka value that's a small number, less than 1, means that that reaction is reactant favored. In other words, a lot of undissociated molecules still left. Which of the following dissociates entirely into metal ions and hydroxide ions in solution? That is B, a strong base. And the key here is that it dissociates entirely into metal ions and hydroxide ions in solution. There are some bases that have hydroxides but are not strong bases, like aluminum hydroxide is not a strong base. But if you have a group 1 metal or a lower group 2 metal, like calcium or strontium or barium, those are going to be strong bases. I may have given this one away. In general, compounds formed from active metals and hydroxide ions are, is it A, strong acids, B, strong bases, C, weak acids, or D, weak bases? Yep, I said it before. Those are strong bases. Again, anything that's an active metal with a hydroxide ion will be a strong base. All right, page 3. Here we're talking about pH. First question, write the simplest form of the chemical equation for the self-ionization of water. There we go. And again, sorry I'm not able to do subscripts with this program, but we have H2O, liquid, yields hydrogen ion and hydroxide ion. Again, very simple. Number 2, write the equilibrium constant expression, KEQ, for this equation. KEQ is equal to the hydrogen ion concentration times the hydroxide ion concentration over the water concentration. But remember that water is a pure substance, and so therefore we'll end up not using water in our final equilibrium constant expression. Now, I think I've given away number 3. So here we go. Write the expression for the equilibrium constant of water, Kw, and go. That's right. Yeah, Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. Why can the concentration of water be ignored in the equilibrium expression for water? Man, I keep answering these beforehand. I got to stop doing that. And go. As I said before, that's because the concentration of water, which is a pure substance, is essentially constant, and we don't use those in our K expressions. All right. What is the numerical value of Kw at 298 Kelvin? Kw at 298 equals 1.0 times 10 to the negative 14th power. We said that for both hydrogen ion and hydroxide ion in pure water, those concentration values are 1 times 10 to the negative 7th, and you combine the two to get 1 times 10 to the negative 14th. But we also said that in any solution, acid or base, that the product of the hydrogen ion concentration and hydroxide ion concentration is always going to be 1 times 10 to the negative 14th. So that's something important to remember. In solution, if the hydroxide ion concentration increases, what happens to the hydrogen ion concentration? The answer, it decreases. Yes, these are inversely related. Number 7, if the concentration of hydroxide ions in solution is 1 times 10 to the negative 6th, what is the hydrogen ion concentration? Okay, so the hydrogen ion concentration can be found by dividing Kw by the hydroxide ion concentration. So hydrogen ion concentration here is equal to 1 times 10 to the negative 14th divided by 1 times 10 to the negative 6th, which gives us a hydrogen ion concentration of 1 times 10 to the negative 8th. Number 8, is the solution in question 7 acidic, basic, or neutral? Explain. It is basic because the OH concentration is greater than the hydrogen ion concentration, right? 1 times 10 to the negative 6, the hydroxide ion concentration is greater than 1 times 10 to the negative 8th. So therefore, it must be basic. All right. In the space of the left, write true if it's true. If it's false, change the italicized word or number to make it true. Number 9. The pH of a solution is the negative logarithm of its hydroxide ion concentration. No, that's not right. It's hydrogen ion concentration. If we wanted pOH, then we would take the negative logarithm of its hydroxide ion concentration. Number 10. Values for pH range from 0 to 14. That's true. That's exactly right. Stomach contents have a pH of 2, which means they are basic. No, that means they are acidic. Remember, acidic is the range from 0 to 7. Number 12. The hydrogen ion concentration in a solution with a pH of 3 is 2 times greater than the hydrogen ion concentration in a solution with a pH of 5. No, they got that way off. Remember, for each point of pH that we change, from 3 to 4, 4 to 5, etc., that's going to give us a tenfold change in concentration. So from 3 to 5, that's a difference of 100 times greater. All right, let's move on. Number 13, the pH of a neutral solution at room temperature equals the pOH of the solution. That's true. Yes, at neutral solutions, pH and pOH are equal. If a pH of a solution is 3, its pOH is 10. Nope, the combination of pH and pOH equals 14, so therefore the pOH must be 11. The pH of a solution with a hydrogen ion content of 1 times 10 to the negative 8th is 8. That's exactly right. If we take the negative log of 1 times 10 to the negative 8th, we would get a pH of 8. That's correct. Number 16, the pH of a solution with an OH of 1 times 10 to the negative 6 is 6. No, the pOH of a solution with an OH content of 1 times 10 to the negative 6 would be 6. So the pH has to be 14 minus 6, or 8. All right. What is the pH of 4.3 times 10 to the negative second molar HCl solution? HCl is a strong acid. All right, so if the pH is equal to the negative log of the hydrogen ion concentration, HCl, since it's a strong acid, will give us exactly 4.3 times 10 to the negative second hydrogen ion concentration. Remember, strong acids dissociate completely, so whatever their molarity is, that is also going to be the concentration of their hydrogen ions. So the pH is equal to negative log of 4.3 times 10 to the negative second, giving us a pH of 1.37. For number 18, we're not going to do this problem, and I want to show you why really quick. The book is mistakenly offering you the suggestion that to find the pH, you'll simply double the amount of hydrogen ion concentration and find the pH that way, since this is a strong acid. However, that is not actually the case. H2SO4, yes, is a strong acid that will dissociate completely to give us hydrogen ion and the hydrogen sulfate ion or bisulfate ion. However, this, which is a conjugate base in this reaction, is not a strong acid. And so therefore we can't just say that it dissociates completely to give us hydrogen ion and the sulfate ion. In fact, it would not be anywhere close to being double the hydrogen concentration when it's all said and done. This is not something I would give you on the test at this time, but most likely we would cover something like this in our college chemistry class. So let's move on. What is the pH of a 2.5 times 10 to the negative fifth molar NaOH solution? NaOH is a strong base. Okay, don't let them trick you on this one. To do this, we need to find the pOH, which involves the hydroxide ion concentration, which is what NaOH would give us, hydroxide ions. So this is going to be the concentration of hydroxide ions. So the pOH is equal to the negative log of 2.5 times 10 to the negative fifth. That gives us a pOH of 4.6. To find the pH, we simply subtract that from 14. So 14 minus 4.6 gives us a pH of 9.4. For number 20, we can't actually take double the concentration of the OH here. It seems that calcium hydroxide, when it does dissolve, does dissociate to give us two OHs, and so therefore we can say the negative log of 7.2 times 10 to the negative 6 instead of 3.6, giving us a pOH of 5.14, which would then give us a pH of 8.86. All right, number 21, indicator paper can be used to measure the pH of a solution. Right. Indicators are substances that are different, yes, colors, depending on the pH of the solution tested. Another way to measure the acidity of the solution is the blank, which uses electrodes placed in solution to directly read the results. Yep, that's the pH meter. pH meter. Okay, page 5, talking about neutralization reactions now. A chemical dye that changes color based on the pH of a solution. Seems like we just saw that. That's A, an acid-base indicator. Number 2, a method for using a neutralization reaction to determine the concentration of a solution. That's G, a titration. We did that in our first video for section 4. Number 3, a reaction in which an acid and a base react to produce a salt and water. That is a neutralization reaction. That's exactly what it does. A solution of known concentration. Well, that would be our standard solution. That's what we use as what we call a titrant, the solution that we find in the burette. An ionic product of an acid-base reaction. A salt is the ionic product. We get a salt and water in a neutralization reaction. The point in a titration in which an indicator changes color. That is what we call our end point, And finally, the stoichiometric point of a titration. What they're saying there is the point in which you have hydrogen ions that are equal to hydroxide ions. That is the equivalence point. All right. Complete the following table indicating the formula and name of the salt formed by a neutralization reaction between the listed acid and the base. The first one's been done for us. We have HCl, so we would take the anion portion of that and combine it with the cation portion of the base, and that gives us KCl, which is potassium chloride. So number 9, what would we make out of H2SO4 and MgOH2? Yep, we'd make magnesium sulfate, MgSO4. The magnesium has a +2 charge, the sulfate has a -2 charge, so they just go together like so in a 1-to-1 fashion, magnesium sulfate. What about the next one? We have H3PO4, so the anion is PO4. The base we have NaOH. What would be the formula and name? That would give us Na3PO4. Remember, sodium has a +1 charge. The phosphate group has a -3 charge. So we need 3 sodiums to match with that phosphate group, and that gives us sodium phosphate. What about nitric acid, HNO3, and iron 3 hydroxide, FeOH3? Well, that would give us iron with a +3 charge because each hydroxide is -1. That means the iron is +3. And the nitrate group is -1. So therefore we need, if we swap and drop, we'd have +3 for the iron, -1 for the nitrate. That means we have 1 iron and 3 nitrates. That's iron 3 nitrate. And finally we have H3PO4. PO4 is the anion. And calcium hydroxide. Calcium is the cation. What do we have? Okay, we have Ca3PO42, calcium with a +2 charge, phosphate with a -3 charge. You swap and drop and you get 3 calciums, 2 phosphate groups, and that's calcium phosphate. Okay. So for the first set here, 13 through 16, we're going to use the numbers 1 through 4 to show the correct sequence of steps when using a pH meter for a titration. And then for 17 through 20, we'll use numbers 5 through 8 to sequence them using an unknown solution. So 13 through 16, let's see. Continue adding the standard solution to the solution of unknown concentration until the equivalence point is reached. The fact that it says continue tells us it's not number 1, right? Let's see, number 14, fill a burette with a standard solution. Number 15, start adding the standard solution slowly with mixing to the solution of unknown concentration, reading the pH at regular intervals. 16, use a pH meter to check the pH of a solution of known volume but unknown concentration. There we go. So that'd probably be our number 1 right there to start off with. Number 2 would most likely be this guy right here. Fill a burette with a standard solution, the titrant, as we call it. And then, 15 and 13, start adding. That would give us 3, right? That would be the third step. Start adding the standard solution slowly. And finally, the last one would be number 4. Continue adding until the equivalence point is reached. All right, so there you go. So 4, 2, 3, 1 would be the order there. Now, for this section, we're going to use 5 through 8. This is when we're actually calculating the concentration of an unknown solution. So, We have the steps: calculate the number of moles of acid or base in the volume of standard solution added. We have used the mole ratio from the balanced equation to calculate the number of moles of reactant in the unknown solution. 19, use the number of moles and volume of the unknown solution to calculate molarity. And 20, write the balanced chemical equation for the neutralization reaction. Well, I think 20 is our place to start. We first need to know what the neutralization reaction is before we can do any kind of calculations. Next, we're going to want to find the moles. Calculate the number of moles of acid or base in the volume of standard solution added. Right, so we will have used a certain amount of acid or base in standard solution, and so we calculate the number of moles of that, knowing the concentration like we do. So then we use the mole ratio from the balanced equation to calculate the number of moles of reactant in the unknown solution. So that one would be 7 right there. 19, use the number of moles and volume of the unknown solution to calculate molarity. Now, folks, you should know, I'm probably not going to have you label the steps in this fashion. If anything, I would ask you to give me some sort of idea of what to do in a titration situation where you can write out the steps yourself. You can remember what we did in the video and something along those lines, but nothing in the way of this matching situation. Wrapping things up with salt hydrolysis. We talked about that at the very end of the chapter. Complete the following concept map using the terms acidic, basic, and neutral. What if we had a salt from a strong acid and a strong base? Yes, the anion from the strong acid would be neutral, and the cation from the strong base would be neutral. Neither one of them are strong enough to hydrolyze water. That conjugate base from the strong acid and the conjugate acid from the strong base are not strong enough to hydrolyze water. Therefore, those ions, the anion and cation, would be neutral. So the salt would be neutral. What about for a strong acid and a weak base? For a strong acid and weak base, the resulting aqueous solution would be acidic. For a strong acid and weak base, recall that strong acids, they give anions that are too weak to do anything to water. So those are neutral. And the weak base gives us a cation from a conjugate acid that's fairly strong. So that cation is strong enough to cause an acidic solution in water. And so neutral plus acidic yields acidic. What about for a weak acid and a strong base? That would be a basic solution. A weak acid would produce a moderately strong conjugate base. That conjugate base would be in the form of an anion that would hydrolyze water, giving OH ions in the process, so that's a basic solution. But the strong base is going to give us a cation that's too weak to hydrolyze water, and therefore it would be neutral. So basic plus neutral gives us basic. So I hope that makes sense to you. If not, again, take a look at the video for Chapter 18, Section 4b, and that should help you out. Finally, true, false. Buffers resist change in pH. That is true. When we have a weak acid with its conjugate base or a weak base with its conjugate acid, yes, they are designed to resist severe changes in pH. 25. A buffer can be a mixture of a weak acid and its conjugate base. I just said it out loud, didn't I? Yes, that's true. That's exactly right. An example of a buffer solution is a mixture of acetic acid and sodium acetate. That's correct. Sodium acetate is the basic salt version of that weak acid. So sodium acetate is a conjugate base, and acetic acid would be the weak acid. So yes, this is a buffer solution. 27. A buffer solution changes pH only a small amount, even if large amounts of acid or base are added. No, that's false. You can only go so far with a buffer. In fact, we talk about a buffer capacity, the capacity that a buffer has until you start seeing major changes in pH. As long as you're using reasonable amounts of that acid or base, it should hold pretty steady. A buffer system should contain considerably more acid than base. That's false as well. Actually, you want to have fairly similar concentrations of acid and conjugate base, or base and conjugate acid. Specific buffer systems should be chosen based on the pH that must be maintained. Sure, that's true. We said that at the very end of the video for section 18.4b. We said that you can actually design a buffer based on a pH situation that you need. So there you have it. That's the end of the study guide for chapter 18. I hope it's been helpful to you. If there's still any questions you may have, please don't hesitate to give me an email and I'll be happy to try to help out. Until I see you next time, God bless.